right, let's look at just a review of the difference between a critical point and an inflection point. Can you think of what the differences are? A critical point is where something critical is happening, right? A maximum, a minimum. And an inflection point is where we're changing concavity, or where we also said the point of diminishing returns. How do you find a critical point? How do you find an inflection point? You got this down, right? Critical point, your first derivative, set equal to 0 and solve for your variable. Inflection point, set your second derivative equal to 0 and solve. What do critical points tell you and what do inflection points tell you? I kind of just mentioned that. Your critical point is where your tangent line, your slope is 0, or where you could have a max and a min. Inflection point is where the concavity changes and the rate is the fastest, which we also call the point of diminishing return. So if you have something like this in your math packet, page 27, it says to sketch this graph, then what you want to do is you want to make a sign diagram for your derivative. So find your derivative first, set it equal to 0. Look always to see if you can factor. I can factor out a 4x. This middle piece in here, this trinomial, remember algebra, right? Coming back to haunt you, I can factor it. And then I set all three of these pieces equal to 0, and I solve for x, and that gives me my critical points. So how do you find critical points? First derivative, set it equal to 0, solve for your variable, and you could have 1, 2, you could have no critical points, right? In this case, I have 3, so I make my sign diagram with my critical points. I pick values in between these intervals to see if they're positive or negative, and I plug those values into my derivative, okay, because the derivative tells me if it's increasing or decreasing. So I plugged in a -2, I got a negative value, which means it's decreasing. I plug in a -0.5 because that would be in between here, so that says this piece is positive, so it's increasing. Plug in a 1 because that's between 0 and 4. I get a negative value, so that says the function is decreasing. And then finally I plug in a 5 and I can see that it's increasing. I would like, when I find critical points, because a point is an XY value, right? Well, these critical points, -1, 0, and 4, are just the X values. So to be able to plot these on a graph, I would actually like the Y values, which says to plug these points, these critical points, these X's, into my original function, and that gives me my actual points. And so now I can kind of sketch this. I can see it's negative. It goes flat, goes positive, goes flat, goes negative, goes flat, and goes positive. I can tell by just looking at this graph that I have some max and some mins, okay, some low points and some high points, and then I can officially graph it and just see what it looks like. So the critical points really help you find these minimum and maximums, and that's what we're going to move into. So now let's look at absolute maxima and minima. So you might be interested in a price or a production level of a commodity. Okay, so certainly you would be interested in maximum profit, or you might even be looking at, you're interested in minimum pollution. So certainly you can see a need for maximum and minimums in many different industries. F of C, so that just means I have a value, I'm evaluating my function, is a local max if my function is less than the value of f of c for x near c. So that just means that f of c is greater than my function when I'm near this value of c. And then of course the reverse, if my value of my function of c is less than my function, then that means it's lower and I would have a minimum. Well, if we look at the entire domain, the only thing that changes here, instead of a local max and min, is we call this an absolute max and min. Now you're going to find your workbook and different places call these different things. Local, sometimes you will see it called a relative max or relative min. Absolute, you'll see called global max and min, and those mean the same thing. So in other words, a local max or min, I'm just in a specific interval near my point, where my absolute max and min, I'm looking at the entire domain. And again here, I've mentioned that this absolute sometimes is called global, and I should put a little note here that local sometimes is called relative. So if I'm looking at this graph and I want to know what the absolute max is, and I want to know what the absolute min is, what do you think it is? If you're looking at this low point and this high point, you're wrong. You know why? Because these arrows say this goes down forever, so it never ends. There is no minimum. This goes up forever, so there is no absolute max or absolute min. However, there is a local max at this f of negative 2 and a local min at f of 2. What's the absolute max or absolute min of this one? Well, I can see that it's going down forever, so there's certainly no minimum, but it's not going to turn because we know what an x squared looks like. And so this actually would be my f of 0, okay, or where y equals 4 would be my absolute max. You have to remember when you're in a math class and they talk about domains and you're like, well, you can't divide by 0, you can't take the square root of a negative number. And in the real world, that probably doesn't make any sense to you, but a restricted domain in an application would be more, you only have so much material. You can only work people so many hours. You can only run a machine so long. And so a lot of times your domain may be restricted for these practical reasons. This extreme value theorem says that a function that is continuous on a closed interval, in other words, I have a restricted domain, has both an absolute max and an absolute min. So if my domain is closed, notice these points are circled in, then I do now have an absolute minimum and an absolute max. These humps right here may be local max and local min, but I'm looking at my entire domain. And I can, of course, shorten this and see, well, now this would be my absolute max because it's the highest point, my absolute min. Absolute max, if I don't go all the way down, it would be at my endpoint. So you can see endpoints can be your absolute max or min. And then finally, this last one, I can see that even if they're even here, I could actually have more than one absolute max or min. So all max and min, if you notice, every one of these pictures occur at a critical point. Critical point, critical point, critical point. You remember what critical points are, right? Or at an endpoint. And so locating these, that's how we find them. We find our critical points, we find our endpoints, and we see which one's the largest for our max and which one's the smallest for our min. So let's go through an example that we want to find our absolute extrema, our max or min, on a closed interval. So the first thing you have to do is make sure it's continuous over that interval. Find the critical numbers in the interval. Then evaluate the endpoint. The largest is the max out of the critical and the endpoints, and the smallest is the minimum. So if I wanted to find the absolute max and absolute min of this function on this interval, -6 to 4, well, first, is it continuous on this interval? Yeah, I know what x cubed looks like, so that's certainly, this is a polynomial, so it's certainly continuous for all values of x. Find the critical numbers. How do you find critical? Set the derivative equal to 0. There's the derivative, 3x squared plus 6x minus 9. I went ahead and factored out a 3. I can see I factored x squared plus 2x minus 3, so I can see my zeros would be at 1 or -3, so those are my critical points. Evaluate at the endpoints. So I'm going to evaluate my endpoints and at my critical points. So I'm evaluating at the function at 1 critical point, -3 critical point, endpoint -6, and endpoint 4. I'm plugging this back into my original function because I want to see where's the absolute max. Well, that would be at the highest value, which would be 69, the largest value of my function. And then I want to see where the minimum would be, which would be the smallest. In this case, the -61. And if I graph this, I can see, because this is a closed interval, that my absolute minimum and my absolute maximum are actually found at these endpoints. And remember what these values are called. These are my critical points, which in this case would be my local max and my local min. Certainly we can have functions that never have a max, they continue on forever, or never have a min. Notice if I have an open interval here, I'm not going to have a max or a min. And then of course notice here, if I have vertical asymptotes, this is going up and down forever. So our second derivative, which is nice, we talked about if our second derivative is positive, concave up, second derivative is negative, concave down. But what happens here is if I look at this and I say, well, I have a critical point here and here. How do I know if it's a max or a min? Well, how I would know is look at the second derivative. So the second derivative test would tell me if it's a max or a min. So the first derivative, where it equals 0, are critical points. The second derivative, if it's positive, okay, at that point, then I have a minimum. If it's negative, then I have a positive. If the second derivative is 0, then the test does not apply. Okay, let's look for the local max and local min of this function. Notice there's no closed interval, so I have no endpoints to deal with. I just want to see if this function somewhere has a max and a min, okay, within this x cubed plus 3x squared minus 9x minus 7, within its domain, which is just for all real numbers. So I find the first derivative, I set it equal to 0. Okay, so we did this already. And notice I got my critical points. So these are still my critical points. Then I find the second derivative. So notice up here I take the derivative of the first derivative. I get my second derivative. I evaluate it at the critical points. So I plug in to my second derivative the critical point x equals 1. That's positive. X equals -3. That's negative. So I know positive means concave up, a minimum. Negative means concave down, a maximum. So that's kind of nice because the critical point just tells you it could be a max or a min. The second derivative tells you if it's a max or a min based off of the sign. So again, I want to actually find the point, so I go back to my original function. I plug in my critical point of 1. I plug in my critical point of -3, and that gives me the actual xy value. And that's what you want, because how are you going to just graph a 1 and a -3, right? You need to know where to put it. And so now I can see my local max and my local min on this function. So the second derivative test for absolute extrema on an open interval is where we're going to look at the second derivative to be able to tell if it's a minimum, if it's positive, or if it's a maximum, if it's negative.